Hello and welcome back to another code session video with, of course, me, James Livesey. Hopefully this video should be much better production value. I know last episode I was using some weird combination of OBS and I want to say Skype with my phone to get my face streamed as like a webcam, but I know that ended up in a very terrible result. This time, hopefully, it should be better. I've got like two cameras pointing at me right now, and I've got three microphones. Hopefully, not too over the top. I'm not sure if that increases or decreases the chance of failure in producing this video. I remember one episode I recorded only to then have to record it all over again because I didn't hit record. We've all been there. Today we're actually be focusing on a programming language that I've been building for the past few months now, since around about February. Today we're actually building support for for loops in the programming language, which is going to be quite an interesting one. I'm going to actually show you the programming language that I've been making and kind of stuff that you can do so far in this video. I know I do ramble a lot, but I thought I'd give you a bit of background beforehand as to why I'm actually even creating a programming language in the first place, not only because it's fun, but there's a reason to it, I should hope. So yeah, this programming language is actually part of a much wider project, I suppose an experimental project, if you will, to basically build a portable computing device that would be kind of pocket sized, so something that you could easily carry around. I know you're thinking, like, James, smartphones exist already. Come on, you were building a smartphone like in 2021, I think. But yeah, 3 years ago. And I know. That is cool and all, working with the Pine phone and everything. But this time I want to try and kind of build a device centered around, like with Blackberries, they've got like the keyboard and the display, and that kind of form factor. I basically want to create something a bit like that, and something which is a lot simpler to build as well, because building a whole smartphone is not an easy task. It's something that I aspire to do. But this device would be a lot simpler. A portable computing device, not necessarily, it doesn't have to do all the things that a smartphone does, but something which you can keep you like entertained, I suppose, keep you company, when you use it, I suppose. And I have been actually prototyping this device already. I'm just gonna start up my overhead camera. Hopefully that should work. Famous last words. Hopefully you can see it. So right here I've got a few things on a breadboard. Hopefully you can see that. Center it in shot. We've got a sharp memory display, which is a very, very nice display, 2.7 inches, all monochrome, but very high resolution. And the best bit about it is it's got the the energy efficiency of e-ink, but with the refresh rate of like a modern LCD display. It's such a fabulous device. This one's actually made by Adafruit, as you can probably see, and they also have a demo on their website to show you just how good that refresh rate is. They can literally play a demo of Bad Apple on this thing at like a really good refresh rate, which you wouldn't really be able to achieve on e-ink displays. Now, of course, in their demo, like the resolution is not very good because they're using an Arduino, and an Arduino doesn't really have that much memory to store, Bad Apple, a movie in it. But it gives you an idea, and I will show you the I'll attempt to show you how good the resolution is on this thing. I'll just plug this in here. It's like USB, isn't it? You have to put it in the right way. Oh. It's so fiddly with these JST connectors, but you'll see right away it's booting up. I'm going to hold this up. Hopefully, yeah. So you might be able to tell it's daylight readable, just like e-ink, in that you need like ambient light to shine on it to be able to read what's going on. And the resolution is probably not that great on my overhead camera, but you should be able to get an idea. Here's a photo of actually what it looks like close up. Full resolution, full HD glory. But in terms of what I've created so far is I've created this kind of prototype user interface which I can navigate like so. Here I'm cycling through a bunch of things, and we've got like a home screen with like different apps on it, which is cool. You can go up and down with these buttons. It's all well and good. I programmed it using CircuitPython, which is a really cool thing. The only problem though is it's a bit slow. Like when I scroll, it takes a good like second to update all the elements on the display and move them. And that's not a fault of the display, it's a fault of the processor. Now the compute chip on here is at ESP32. This is the S2 version. In the final thing I'd be using an S3. I've currently got an S3 over here, but that's kind of wired up to a completely different project I was working on. I don't want to take that apart. But this is the S2, and it's a similar thing with the S3 in that CircuitPython and the libraries that I'm using, and then the abstractions that I'm doing on top of those libraries, is making it really slow. And yeah, it's abstraction over abstraction, and really I kind of just want to get rid of that and build it from the bottom up myself, really, which is what I'm trying to do. Now, yeah, you might say that I could just write it in C or C++. Like, if I were to write it in any of those, program languages, it would be so much faster. But the problem with that is that you can't then write apps which can then easily be loaded into the MCU, like especially with microcontrollers, like they have to be all flashed, like their program space has to be flashed in their entirety, and especially on Arduino, that's the only bit which programs can be read from. So my solution is to build a programming language and to basically build a bytecode interpreter which can run on this thing. Ambitious, I know, but then it'll allow you to run loads of apps on it, and you can download third-party apps all written in my programming language. Well, the display has a few updating issues. I think that's probably because I'm doing it on a breadboard. But yeah, you get the point. It's really slow, especially if I open an app. This is just a demo app. It took a good 3 seconds there to load it up. This is pretty cool. It's showing the current time, if you can actually see it on the camera, because my hand keeps moving about. And we can navigate through all the the UI elements, which is cool. But again, it's just really laggy, and I want to improve that and build my own like abstractions. Have complete control over the whole system, which would really be really cool. So that was a demonstration of the kind of thing that I want to build. It'd have its advantages, like battery efficiency, for example. The ESP32, especially the S3 models rather, they use about 25 milliamps of power, which is a very small amount. That's 25 milliamps without using the radio modules, which are on board. So no Wi-Fi, no Bluetooth. When you do use Wi-Fi and Bluetooth, it's about 100 milliamps. But with them turned off, it's 25 milliamps. And when it's in light sleep mode, which is what it would be doing most of the time anyway, when it's in your pocket, that's only 2 milliamps. And my battery, I'm not sure if you can read that. Start up my camera again. My battery is rated for, you could probably read it, I don't know, 3,000 milliamp hours. So you're talking when it's in, light sleep mode, that's like 1,500 hours on sleep without charge. That is 2 months um, of being on sleep without charge. Theoretically, obviously, I think it'd be a bit higher, a bit lower than that in practice. But having a device, like, you get the idea. Like, having a device with that much power efficiency that it can last for months on sleep. That is what I want to achieve. That would make a good device, which is energy efficient. Not to mention it'll be modular. That's kind of what I want to go for. You'll be able to plug in different things. So if you did want to, communicate with the outside world with a cellular modem or even like Meshtastic, you'll be able to plug in a module and then you'll be able to talk with that. And we could probably save the environment here while we're doing it. Like, e-waste reduction would be really good. You're not spending so many valuable resources making this thing. It'd be really cool to build that, and hopefully I can do that. But anyway, I digress. Let's get on to the actual programming language now, which is why you came to this video. No doubt people in the comments will be leaving timestamps to jump to this point in the video. So you'll be able to see on my screen here, this is Visual Studio Code, of course, with my Voxel programming language project loaded up. Yeah, I've called it Voxel, mainly because it's a name which hasn't been taken really. So yeah, there's a lot of code here, a lot going on, as you can imagine. The majority of the programming language is written in C, basically. So there are different components to this. So there's the bytecode interpreter, which is what's going to be running on, the target platform where our program will be running. And that's all written in C. That way it's nice and portable. It's literally, if you see here, we've literally just got this massive like giga file called libvoxel.h, and that is just a single C header, which you can then just include in your C program, and that contains everything that we need to run this bytecode interpreter. And you might be thinking that's a lot of code for a bytecode interpreter. And that's because it's all dynamically typed. I've decided to go for dynamic typing, so you don't have to declare types and everything. It's just store this thing in a variable. That's kind of what I'm going for. So a lot of that is to ensure that you can create things. If you go to, I did see it a second ago. Yeah. So for example, to create a string, we call this function called new string, and that allocates in memory like a data structure which holds information such as the size and the bytes and everything, and also the fact that it is a string. So there's a lot going on for each like type in the programming language. There's basically something like this, and we do the same for destroying the strings somewhere. I might have gone past it. Destroy string. Here we are. And that's freeing it up and everything. So yeah, there's a lot going on for just the bytecode interpreter. Elsewhere we've got things like setting values of objects. Yeah, this programming language already can support lists, it can support objects, it supports all sorts right now. Not quite classes yet, but it can do functions, it can do closures just about, which is what I implemented yesterday. I can't believe I implemented closures before I even implemented for loops. That's like a strange way of going about it, but yeah, we've got all the list operations, so you can join lists, you can get their lengths, you can insert into a list at a specific index. You can do all sorts right now. I haven't actually shown you what the code actually looks like in terms of what does a voxel program look like. Well, this is like an example file which contains all the features that I've implemented so far. So to give you a bit of a whistle-stop tour, you can do printing. You can basically do these kind of system call things, which hooks into C built-in functions that you can create. That way, for your target platform, you can call a syscall and it will do a thing specific to that target platform, basically. So syscall log will write something to std out. Standard output. So that is what that does. And then you can create functions like function hello. Very, very simple. The syntax is very, very similar to JavaScript actually, which is kind of what I've gone for. It's not completely JavaScript because I know JavaScript has some very weird things going on, such as this. It's designed to be very similar, just to aid with familiarity, so that people don't have a massive learning curve when learning how to use this programming language. And yeah, like I said, we've got while loops. We don't have for loops yet, but we have while loops. If statements, else if, all the logical operators, and expression stuff for that. And then we've got lists, as I just showed you in the libvoxel file, and all the operations to do with that. Objects as well. You can actually even define an object like that, just like in JavaScript, which is pretty neat. It can do a lot so far, which is not bad for what is now April. It's like 2 months odd worth of work that I've done, which is not bad, among other things that I've been doing. You can do imports as well. It's currently basic at the moment. You can't actually call a function within an import, but you can import code. Well, that's something I'll show you in a sec. So yeah, this all basically is compiled down into bytecode. This is the bytecode for the program that I just showed you. There's a lot going on. Ideally, I need to do some optimization to remove out bits which are never executed, but that is something that I can work on at some point. And it's designed to be relatively readable. So strings start with a double quote character, and then you've got the string, which is then null terminated. And then these question marks basically mean get this variable. And yeah, it's generally not too hard to follow when you're debugging it, and that's kind of the idea. And yeah, this thing is portable, so you can write this. This is just a hello example of how to write an interpreter. Here we can create a new voxel context. You can then define built-ins like the log syscall that I did show you, and then add, which I defined here to add 2 numbers. So that basically calls that when you run the add syscall. And then when you're loading the code, you can then just init it, and then while true, execute it really. And this code is actually a bit out of date. For the actual runtime that I've been working on, it's about this big. It's literally just importing Studio, and then this config file here, which I just use as Studio. And then that allows you to just create a new context, load in the file, which we do here, and then while we've got a context that is currently active, literally just step through forever until we're done, in which case we can then exit our interpreter. So to give you a real life demo, I can go down. Actually, I should probably write this all. So probably put our thingies behind. So I've written the compiler currently in JavaScript, and it's using Deno as the runtime. That is something which I'll then rewrite in Voxel itself, which would be really cool to showcase. But it's very simple. We just simply go examples, and then hello.vxl -o, so a bit like GCC really, examples / build / hello.vxc. When we run that, going wrong on camera. How did I do it? Okay, let's just pretend that I have run this command, which is in the bash history. I think I misspelled right, that's why. So that basically, yeah, it resolves our imports. It then parses the core namespace, which is to do with a file which contains code which is always present in all Voxel programs. It's basically a bit of boilerplate to enable a bunch of functionality. And then we pass our files, we generate like the bytecode for it, and then it's written to hello.vxc. And then we can then run this by going runtime build / voxel, and then we simply just go examples / build / hello.vxc. And there we go. This is the output. There's a lot going on. So, you know, we have our, like, this is a message from a .vxl file, just to say it's working. We do a countdown, as you might have saw in hello.voxel. Here we go, here's our countdown. This is obviously something which we'll be implementing with for loops. And then fizzbuzz, it's really cool to see that working. And while list operations and object rotation operations, etc., etc. So it's a bit like Java, really, in that you have a compiler and then you have a runtime to run the bytecode on desktop, anyway, at least. So that's how you run a program. Now for loops. Let's get to the main meat of this video, shall we? We're nearly there. Now, I'm not expecting to do any changes to the bytecode interpreter. As far as I'm aware, like, it should have the necessary support so far to enable us to implement for loops. You did just see like while loops being able to do like fizzbuzz and stuff. So, you know, it's possible. Just that you have to, you know, use while loops right now instead of for loops. So it's purely a change that we're making to the compiler, really. So we shall dive right in. So our compiler, as I said, is written all in JavaScript, and for loop is a statement, of course. It's a type of statement. So it's really, we're really going to be implementing it here. Right now, as you can see, we've got things like functions and if statements implemented. This is where while loops are implemented. So here we basically pass the tokens. So we have a tokenizer stage which runs a bunch of regex to formulate the tokens and add them to like an array. And then here we basically have an abstract syntax tree node, which basically expects, you know, a bunch of tokens. So our parser basically looks at all the different candidates for abstract syntax tree nodes, or AST nodes, I should call them from now on. And, you know, we've got this kind of match queries, like variable here, or I suppose constant, almost variable. And that basically says this type of node applies when the current tokens that we have starts with this. So when our tokens start with while at the start, then we know that we're going to be you know, creating a while loop. So then here we then basically run this create static method, which creates a new instance, and then it expects a bunch of tokens of different types to build our while loop. So here we eat the yes, the terminology is eating tokens. We eat our while token, so the default argument is just to eat that one. And then we eat an opening bracket, from which we then expect an expression. So, you know, while x equals y, so that x equals y in terms of syntax, that's our expression node. And then we eat the closing bracket. And, you know, if the tokens deviate from this, then that's when we throw a syntax error, such as, to give you a demo, if we run our compiler again, you can see that I've created like a nice kind of output to say, oh, we expected a closing bracket, but we got a bracket instead. This is not a very good example, is it? Because a bracket it's a different type of bracket that we're expecting. We're expecting a we got a curly brace bracket, but we were expecting a parentheses bracket, paren. What do they call it in America? That. So yeah, it shows you where you've gone wrong, which is quite good. Really, I should make it so that you don't have to add those brackets. I don't think for if statements we even check for that. Oh no, we do. Okay, fair enough. It's probably something, you know, not everyone likes typing in those brackets. Like, I think it's Rust which doesn't have them, or it's like optional or something. I can't remember. So I might make that optional as well. I prefer having them though, so that's what I did here. So after that, we then expect a statement block, which is what we execute while the condition is true, of course. And then we have these symbols which we generate, which act as like markers in our bytecode to say, okay, so if the condition is false, then we need to skip the statement. So that's just a simple case of jumping to an offset, which is named by that symbol there. And then we've got our repeat loop symbol, which is basically at the end of a statement to go back and check our condition again. So here we generate the bytecode when this method is called. And what we actually do is we first define like the markers that we can then jump to, and they are relative to the current program counter, if you were, as I suppose you could say, or like program position, I think is what I've referred to it as. So we define like, okay, so our skip loop symbol, while loop, while skip as it's called, we generate the code for that, which becomes its own entity. We then write a byte, which is kind of like a bytecode command. This thing is stack based, by the way, so here we're pushing the symbol first, and then we're saying like we want a position reference, so forward from the current position, and then our argument is basically all the lengths of the above added together so that we arrive just after the while loop if we want to skip. And then repeat loop is basically going back right to the start. So once the repeat loop has been defined, we're basically jumping to here, and the not condition code is basically getting our condition, which is the first child that we eat here, which is our expression node, and then we not it. And the reason why we do that is so that if it's false, that becomes true, and then that means we can do a conditional jump, a conditional jump, which is jump if truthy. Bit of a tongue twister. We jump if truthy if the inverse of the condition is true. So that's when we skip. And then the repeat loop goes back to the skip loop. No, it goes back to the not condition again to check it again. So that's how a while loop works. So we're going to start implementing a for loop. And I'm just going to write out how we're going to do that on my camera here, which might need a bit of adjustment. There we go. Perfect. Hopefully you'll be able to read my writing. I've created some fancy diagrams. This is how the type system works if you want to quickly see that. Bunch of other stuff, closures. So what we want to do is we want to have our for loop body, which here I call the loop code for the while loop. Here it's going to be I suppose it's also going to be called the loop code. So that is the thing which is kind of in the middle of the code that we generate. Let's actually write out a for loop in terms of the syntax. So for var I equals 0, I is less than 5. Now Voxel doesn't quite have the concept of plus plus yet, or plus equals, so we have to go I equals I plus 1. So here is our loop code, which will be in the middle here between our curly brace brackets. This condition here, not condition, this statement here is basically going to be our start statement. This is going to be our stop condition, and this is going to be our step statement. So we're basically going to divide our statements here by their purpose. So we've got our loop code, which is there. We first need to run the start code, or the start statement, and then ideally we probably want to then check the stop statement. I should probably move this down a bit. We want to check the stop statement because on the first run, if the stop statement is false to begin with, we don't want to execute the loop code at all. So we have to skip all of that. So we run our start statement. We want to go stop condition like that. And then we want to do the same as our while loop. So if it's false, jump to, and then we're going to be jumping to past our loop code. So that's where we'll do the markers as I mentioned. So that will be, I think I called it skip loop. And then we've got a loop code, and then we've got our step code to execute, which of course is going to be the loop after the loop code in any case. JavaScript calls it the after for, according to MDN docs, which is a bit weird. I'm going to call it the step. So we immediately execute the step statement. Actually, I need to think about for loops now. So in terms of our execution, this is going to produce what? If we produce 0, 1, 2, 3, 4. So the problem is with this step statement is, because I'm thinking about how would that interact with the stop condition. No, I think it'd be alright, because if we go like 0, we define 0 here, we then get to the stop condition, 0 is less than 5, so that means that we continue. So if it's true, we go to the loop code, and then the step statement is run, that becomes 1, we go back to the stop condition, 1 is less than 5, and then we get to 4 is less than 5, that's fine, loop code, step statement 5 is less than 5, which is false, so then okay, so that should be fine. So that's our step statement, and then after that we want to then jump back to our stop condition. So let me think. So in the while loop we called it the repeat loop. So jump 2. I hope you can actually see this because I haven't actually checked my overhead camera. Repeat loop. So that should then jump to here. So here we'll have our repeat loop like that, and then we'll have our skip loop here. And that's basically, you know, continuing on past the whole thing. So that is how a for loop would work. You go through, you go, yep. You repeat these lot until our stop statement is false. We get to here, we jump to there, and we continue the rest of the program. And I don't think we have to worry about garbage collecting or, like, you know, deleting our statement here. It's not like scoped or anything. It's scoped to the current, like, function statement. So I think that's true for JavaScript and all the C-like programming languages anyway. So that should be fine as far as I'm aware. So I'm gonna refer to that later, of course, for when I inevitably get stuck. So we'll go. We'll basically do what we've done here. I'm just going to copy that because it's very practically the same. So while loop would become for loop, if I can spell, for loop. The token would be for. Now, for this we need to actually define the keyword token in our tokenizer, because otherwise it will just not match and it'll think it's just an identifier or like a variable name, of course. So I'll just put this at the end here, like that. So that should hopefully match that now. And then we've got our match code, we've got our skip and repeat loop symbols, which we're going to be reusing for our for loop. We need to go static create. This is going to be the quickest thing in the world, I feel. Like, I think I've done more explanation about how it's going to work than it's actually going to take to implement. But, so we eat our for token. We then open our bracket. This is where we need to then get each statement individually. So really I'm going to check again. So get to the right page. Really our start and now you can see really our start and step statements are statements. The middle one is more of a condition, so an expression rather than a statement per se, really, because these two are executing and we're not really caring about the result. But this middle one, we are actually getting a result that we want to check the condition for, if that makes sense. So we will be checking for statement nodes. So we're currently in the statements for module right now. So statement node. We could do a statement block node. Would that be weird if you have like for and then like I equals naught, j equals naught. Let's just program language set to JavaScript. Well, JavaScript doesn't like it. And then you can go like I++, j++. Like, would that be weird? I know that the syntax is erroring like here. Obviously, VS Code doesn't like that. In JavaScript, what you would actually write is for I equals naught, j, note the comma there. I is less than 5, I++, j++. I'm not sure how you actually do the pluses there like that. I don't know if that's valid JavaScript, but I do know that you can use a comma here to denote like two variables that you're defining in the same statement. So actually for Voxel, that might be more useful. Obviously the syntax would be like that. That would be useful, but then we've got the issue of having the semicolons at the end, which I'm not sure how well it would be able to then capture that and that. I'm going to look at what a statement node does. Statement node. This is really big now. Let's reset that. Reset my zoom to how it normally is. There we go. I can see more of my code now. So a statement node. Where do we eat a? What do I call it? Where do we eat one of these statement delimiters? We eat it in a statement block node, so maybe we shouldn't then, because that would be annoying. Okay, so yeah, we're not we're not going to do this first type. Goodbye. We're just going to have single statements. I think that makes sense rather than statement blocks. So statement node is our first child. And then we can go a delimiter. Oh, we need to go. It's not a type of AST node. It's a token. Statement delimiter token. That's the one. And then we're gonna basically do that again, like this. But our stop condition is not a statement, so that can be an expression node instead of a statement. And we have to go expressions dot that because it's defined elsewhere. So that is that. And then we've got our statement block node, and then we've got our symbols that we define. And the reason why we define symbols actually is because we do have mangling, which basically means that when we're doing our compilation, and I just want to check that, yeah, we did fix that while loop earlier, so we don't get an error. When we do our compilation, if we go no mangle at the end, we can then look at our bytecode that we generate in our hex editor, and you'll see that it's a lot more verbose now. We can actually see, like, we've got oh god, we can see we've got things like, where's a good example? Do we have a while thingy? Yeah, so while skip 293 is one of those markers. But as you can see in a bytecode, it's very verbose, and that's taking up a lot of bytes. So actually what we do is we do have a process called mangling, which converts this gargantuan of a file, which is, what, 3 kilobytes? It basically renames all the symbols to numbers, and numbers are much easier to, to store in memory compared to strings. So, and in fact, it's actually more efficient in terms of the bytecode syntax that's available to you. So if we run it now, everything gets replaced. You can see that the only strings that you can see are string literals now, so not like identifier names. And this is... Was I reading the wrong thing earlier? Okay, so the last byte is 3.6 kilobytes, I'd say. If we do no mangle... Okay, there's a lot more. I was reading the wrong thing. Yeah, so we're talking about a 6.9 kilobyte file. Almost 7 kilobytes. But then if we do mangling, we're only doing 3.6 kilobytes. So that's like, what? Half, almost half, just by renaming all variables to number token, not tokens, number. Yeah, number tokens rather than strings. So that's why we kind of generate these symbol names. And in fact, in our namespaces, you can see that we do mangle everything. So mangle symbols, which is this function here, and we've basically got a counter which then increments for each symbol, and we actually do sort all the symbols. So the most common symbols are smaller numbers, so the first 256 symbols are only 1 bit in terms of width, and then the less common symbols might overflow into 2 bits. So in that case, the bytecode uses a 2-bit representation, etc. So we're trying to be a bit efficient where we can in the name of optimization. How long have we been going for? 44 minutes. Wow. So repeat loops symbol. So as far as parsing is concerned, that's okay in my opinion. It's now time for code generation, and we've got a not condition. Now our children are going to be different, so I'm going to actually define these. So we've got our start statement equals our first child. We then got followed by our stop condition, number 1, and then we've got our step statement, number 2, and then finally we do have our loop, I guess, block, or loop statement block, I guess we could call it, is number 3. And I'm actually going to use that in our while loop because it's actually much nicer. Loop condition, let's call it for a while loop. Get them in like that, just for consistency, of course. So our not condition is going to be checking the stop condition, which stops our loop. And then the loop code is just going to be using loop statement block. So that's all good. So the skip loop code will be well, how will we be coordinating that? Okay, the not condition. So yeah, in terms of execution order, so this is where it gets a bit tricky, really. So start code, let's call it. It's just a simple case of doing that, really. In fact, it's probably simpler just to not join anything, really. So that gets executed first regardless of everything. It's just a, I suppose, syntactic sugar almost. So I'll start code, and then we want to get the stop condition and then not it, so that if it's false it becomes true, which means skip to the end of the loop. And then we've got our definitions, of course. So it's not, that's a skip loop. We then loop. Underneath the loop, as in the statement that we're executing, we should then run our step statement. So step code equals code, or step statement dot generate code, rather. If I can spell. And then once we've done the step code, we then want to repeat back in again, and I just messed up my hoodie. And that's pretty simple. Repeat loop definition code. We want to start back up at there, not condition code. So I'll repeat loop code. Yeah. That makes sense, I guess. Okay. Repeat loop definition code. Yeah, those define it. So that's fine. So this is the bit which I personally think is a bit tricky. It's trying to work out the offsets to jump forwards by. And in this case, we are going to skip loop definition code. We want to skip past the start code we don't care about. That's before the definition. So we basically want the skip loop to factor in the length of that, and that. So I think we pretty much had it perfect apart from the step. So we've got that one, as you can see by the highlightings as they go across. We've got that one, got that one, got that one, which should be, let's put the casing on that. Let's start again. So we've got that one, we got that one, we got that one, we got that one, we got that one. We don't have this one, which we basically need to add in. And then we've got that one there as well. So that's all good. I think that would work. Oh, we need to check our repeat loop code. Yeah, okay, yeah, that should work. In my humble opinion. Let's give that a try. So I'm actually going to create a test case for this because that's generally actually let's just modify our this. Let's actually go for I is less than equal yeah, and then I equals I plus 1. So you remove our step condition that we had to create in our while loop, and then let's see if that works. So I'm going to run my this command, which basically does the compilation immediately followed by building the runtime, which won't have changed here, and then immediately followed by running Voxel, the runtime. And we have a syntax error, which is fair enough because we haven't actually added this for loop node. We haven't actually told our AST parser about it yet, so that really needs to just go here. So we've got, our import statements, functions, if statements, blah blah blah. I might be moving functions into an expression actually later on, not today though. So let's run it now. It works straight away. That's pretty good. That's pretty good. So yeah, look, 1, 2, fizz 4, buzz, fizz 7, 8, fizz buzz 11, fizz 13, 14, fizz buzz, and that's 15. That's 1 to 15, which is perfect. Let's create. It's rare that something actually works straight away. I normally have to run it multiple times, but it does happen on occasion, and that feels really good. So let's actually create a test case for this, because it's important to make sure that our code works when we make future changes. So I equals 0, I is less than. Let's do a simple for loop for now. Syscall log I or log \n. So that should print 0 to 5. So we need to create an expected output, which will leave blank just to see. So if we go test.sh, yeah, clearly I need to implement that. This is tricking me. Yeah, I equals I plus 1. That needs implementing, of course. So yeah, we get 0, 1, 2, 3, 4. So we'll expect that, and we hopefully put a new line there. We hopefully should see it as a pass. The reason why it takes 3 or 4 seconds to run those test cases is because it's actually for each test case is actually then running the test case in a while loop, and that's so you can then check for any memory leaks. Which has always been a thing which I'm always chasing after, especially for this project. So, for example, this caused a memory leak not too long ago. To demonstrate, I'm actually going to modify our function node. If we forget to say pop something off the stack, pop a value off the stack in our interpreter, the stack's going to just constantly grow. So if we run our test cases, we'll see that hopefully the closure test will fail, although it failed because of a value which wasn't being expected anyway. Okay, what about if I remove it from here? It's hard to generate a valid test case. Okay, I'll go to core.h, which generates our closures, and I'll just make things not garbage collected. That'll demonstrate it. So yeah, here you can see that it's detected a memory leak by running the same program in a while loop. So basically, for loops, main.loop.pxl. Yeah, it basically generates. So it turns this into a while true version, and then generates bytecode for that. when it runs that, it will then detect like, okay, this is the initial memory that's used after 1 second of execution, and then this is the memory that's used after 3 seconds of execution, I want to say. Yeah, after 3 seconds. It waits 2 seconds and then it checks again. So it's basically just trying to compare like the memory usage of that, and if they're not equal, then clearly there's some like memory issue, or which means that there's a potential memory leak to investigate. So actually pretty useful. I only implemented it a few days ago. I'll just revert that back now so that doesn't become annoying, and everything should pass now. There we go. Okay, so what I'm going to try with our for loops is I want to go let's do a nested for loop. Ooh. Let's do the classic like coordinate matrix. So y equals 0, y is less than, what should we go for? 16? It's a nice number. 1. Okay. And then let's put our x variable in here. I need to remember. Yeah, you don't need spaces around like the plus. Like you can do that, but I prefer spaces. It's more readable. Let's just call log. Let's not do 16 because that's going to be a pain to implement. Let's do 4. Log x. We should probably log just to separate out our output. X and then x. You can tell that it's actually much easier to write this than C because you don't have to battle with types. I will make it easier to like do these logs, maybe through like argument length checking or something. It's theoretically possible right now, but let's run that, see what it comes out with. Ooh, okay. No, 1, 2, 3. Yeah. So that would be perfect for like graphics applications, for example. Although you probably want to do that in a buffer anyway, but for iterating over stuff like that, that's pretty cool. Let's do one where the condition changes partway through. So I'm running out of letters to use, so let's go A. Equals 0, 4. I don't know. Can we do that? Probably not. That's something worth implementing later, but I don't really care right now. We could just put 4 null. We'll see what happens actually in the first place. I think it might error, but we'll see. A equal. We could actually change that in our code. That's something to fix. Oh, we're running up to an hour now. If you're still watching, then thanks. You probably should also go to sleep if it's the evening. A is less than B. A. Let's see what happens if we go like this, and then let's just call log A. And then what we're going to do is we're going to decrement B. What happens there? So this statement will basically be changing. I think it should be fine. It'll be fine. So there's a failure here, which is a VxBuild source error. VxBuild is our compiler, by the way, and it's complaining that doesn't exist. So we'll make them optional, because why not? Well, actually, we'll assess how easy it is to make them optional. Here we have our parser. So that's for the function node. That's the wrong place. No wonder I feel disorientated. Here we have our statement node, expression node, and statement node. So expect child by matching. I'm going to actually look into the definition of this. Could I check for an empty? Oh yeah, I can use add child by matching. So let's do that, and then the fallback would be we just do nothing, or we should just like execute a null token, which will just do nothing. Yeah, although the condition we'd want to do true. If you know what I mean. You probably don't by what I just said just then, but we'll make them optional by going if add child by matching, or if not that, then we just go this instance.children.push, and then I guess a type of expression which says null. Got this node, we've got a thing node. We could. I'm gonna add a method which lets us just create nulls. So I don't think our namespace really matters in this case. So yeah, let's do that. So expressions create null. We'll create literal. I don't know what to call it. Create yeah. Actually, do we even need to? Yeah, before we do actually. Yeah, no, okay. I don't think that's a good name for it. Yeah, half the problem is trying to come up with names of things. Create. Yeah. Does that make sense with like string literals and not really? Ah, naming things. It's already 1 hour ahead and you're still watching. What are you doing with your life? Create literal. This is where I think hard and come up with a solution. Create by value. Yeah. If you've got a better name, pop it in the comments below. As they say. So that'll be null. And in a similar way, we basically going to do the same thing. Except for this one is going to be true. And this one is going to be null again. So null, when we execute that as a statement, it just does nothing, unsurprisingly. So that's what I'm doing there. So hopefully that should work now. Still get a expected import statement or function declaration or if statement or while loop or for loop or return statement or any type of statement. Some of these error messages need improvement. So how come that's happening? Let's go back to the definition. Do not expecting it, which is where that does its thing. If not, we do not show error, so it can be seen. You got statement delimiter instead. Yeah, you did, because that's what I want. Selected action child. Yeah, because if it's not added child, then yeah, for loop node. so we do check that kind of thing. Oh, because we do need to then... No, we don't. That's what I'm saying. Let's just print out all the tokens that we expect then. It's a bit ugly, the output. Oh my god, there's a lot of tokens. Just see what their names are. Blimey, there's statement limits token. Yeah, okay. So that's what we expect. Unless we are doing it. No, we're not. Got to end, got to end, got to end. Well, yeah, it did in the first instances, but... This is definitely an efficient way of debugging. Open and it fails there. So I can imagine it, if we move this up to here, it probably won't like that. Yeah, so it's failing there. The add child by matching should not output an error. Oh, is it because I've constructed a match child? I reckon. Oh no. Oh my. That's a lot. Ah. Yeah, so it errors there. We're not expecting a child by matching. We are adding a child by matching. See what function that actually is calling. Function add child by matching. Can you actually like see the code behind it? Please. Yeah. Return null. Okay. So that is a function. So I think for our test we'll just delete that for now, and then go true. Yeah. Okay. Okay. It really doesn't like it, does it? Statement node. Oh, because we are in the statement node. And then that expects child by matching. Ah. So I think what I'll do is that or a statement limiter node. Token rather. Oh well. How do we match a... Oh, we could do the maybe thing that I did. If yeah, let's do that. So you would be expecting a child by matching now, but only if we don't expect it. Okay. There is method to my madness. So if maybe eat, so maybe basically allows us to check the next token and then eat it only if it is what we match it. If not, then it just returns false. So if we see a statement delimiter token, then we will if we see a statement delimiter token, then we'll add null. But if not, our default, like our preferred path is to basically eat the statement node, and then under that we then want to eat the statement delimiter token. You got me? Yeah. So really we just need to delete these now and then repeat as desired. Bit messy. Expression node. Bit messy, but I think we are there. Yeah, it does look a bit repetitive, but I think that'll be fine because we've got this thing in the middle which kind of tries to spanner in the works, so to say. And it didn't look like that. It expected it. Oh yeah, okay. So if we expect a bracket token instead of a statement delimiter token on the last one, we would basically want to eat that because we're not ending a statement delimiter token there. Yeah, so yeah, our output is obviously not expected yet. We'll run that, see what happens. Okay, nice. So yeah, that's all working now. If we were to remove these, then it would then run forever. So if we do that, it's stuck. And the test thing won't print out the output now because it's not checking for it. If you were to actually go blah 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 build tests / for loops. Come on. Oh, it's test / for loops / main.pxl -o for loops / so if you run it outside the test environment, test for loops / main.vxc, it will constantly print 0. And if we were to go a equals a plus 1, that should work. Should it? If we were to do that, it would go. Why isn't it incrementing a? Could be messing with that. Let's call log a. If this was like a while loop, something's not right here. Okay, let's refer to our hello world code. Count -1. Yeah, what happens if we subtract? Nope. It's even referring to the right. It's not even referring to the right variable. Let's do a head. Because I feel like it starts off null. Oh. Oh yeah. Okay, yeah. No, it doesn't start off with null. That's strange. So A clearly doesn't exist inside the scope. I thought we just fixed that. What's the computer doing? expected bracket, but got instead. Yeah. Unless it wants like spaces, which doesn't, because it's not meant to anyway. A equals naught. Expected. Oh, while loop. That would explain it. So don't know how it's still naught. How are they doing up here? Like exactly the same structure. Is it because we define A outside the loop? No? This is bizarre. Let's actually do that so it makes it a thing. It's because I'm running the same code again and again, aren't I? And I'm not compiling it. I reckon that, I bet that's what's happening. Or it's not. What? I'm so confused. You can actually in a Voxel do return there, so well, I thought you could. Are we building the right thing? Test for loops main.voxel vxc. I think I've broken something, haven't I? Yeah, it's probably broken in terms of this thing, isn't it? It's because if you don't want to so if we revert to the default behavior of doing that, it doesn't like that. Okay, yeah, understandable, really. This is why we write tests. Statement node, expression node, statement node. I should have probably committed this so I could see my history, but clicking this to 8 as expected. I'm going to hold down my Control-Z keys so that I can get back to what we originally had. This is what we started with. So how did I get it working in the first place? Okay, start with that. What? Rather. This is working there. Builds.js main. Okay, so in that configuration, it's fine. I'm forgetting some sort of crucial compilation step in my own. Run it, allow read, allow write. Because of writing to this file here. I can't believe it almost took me as long as when I was trying to figure out how to do the old canvas thing in LibGeoS when I was accidentally writing not to .data but to write into the canvas object itself or something, so that's why the pixels weren't shown. Literally a case of that. So I'll remove that and see if it works in this case, I guess. So that's all the conditions, and then look at that, it's counting up really quickly. Probably not as quickly as Python, but yeah, that's what I expect. And that means that we can do what we originally intended it to do, which was, I can't remember, so I'll let my computer tell me. That. Yeah. And then if we remove this bit, it doesn't increment at all. Which is fair enough, and B decreases, okay. If we remove this bit, it'll always be true. Now, Voxel doesn't have a way of breaking out of a loop yet. That's something I need to do. But yeah, it's pretty cool. I would say that in my books, let's actually copy that output so that we can then put in our expected log. I would say in my books that is done, which is cool. We implemented for loops. Now, of course, we didn't implement like for thing in object or like thing in array yet, like that kind of syntax. We've only implemented like incrementing variables or like, yeah, start, stop, step conditions, you know, structure. So, but I would call that a win in my books for now, because for the other type of for loop, I think that would require iterators, and that is something which I'll probably implement when I get classes working, which I'm very close to getting classes working. I haven't created the syntax yet. I haven't done some sort of prototyping thing yet, but I do have objects which can act like classes. In fact, when you look at some of my demos, you can actually see that it would be under here. You can actually see that you can reference. Can you see it in here? No, it's a bit outdated. Okay, I'll go to my hello code. You can see, hopefully, yeah, you can do this dot value, and then that sets. So structured dot method equals method. This method goes in here. This refers to structured. So at least that's implemented. So I'm very excited about getting classes working, because that is a huge milestone alongside getting imports to work, hopefully soon, towards then getting Voxel to have its own compiler written in itself, which would be really cool. But I would say for now, let's just review our code. Yeah, that looks alright for FizzBuzz. That looks alright for our expected values, and I think it ran fine. We should run our testing again. No errors right now, and yeah, it's all passed, so that's all good. Main.vxl, yeah, this is for our for loops in terms of testing. Create by value, yeah, and then this is the while loop implementation, so not too much, but a good session. I reckon I could probably implement this in about half an hour, as opposed to 1 hour 25 minutes almost. And then we've got that as well. So implement for loop syntax using start, stop, and step. I guess. Yeah, that makes sense. Okay, cool. Let's get that committed. We are this bit closer to like actually realizing this device here it's optimum form. Oh, it'd be really cool if I get this working to an advanced level. So far, it's pretty advanced already. I'm pleased by. Yeah, this is me being pedantic. I don't like having two lines like that. Move unnecessary line. Blank line. I don't know if that's a spelling for necessary. I think it is. So if it's two C's or two S's or what? That'll do. Nobody will notice. But yeah, I'm looking forward to actually trying to get this device working as expected, and having something you can carry around and write a bit of code on. You'd be able to chat with friends. You could do social media if you really wanted to, play games if people start releasing games. Yeah, I'm excited. Thanks for watching this video. I know it's been almost an hour and a half, unless you just skipped to the end bit, which fair enough. you didn't miss too much. If you really like this video, I would really appreciate it if you did subscribe to my channel, because there'll be future code sessions like this one, probably relating to the Voxel programming language, maybe something else relating to this project, maybe even something written in Voxel. That'll probably be a project. I don't know, I might do a video of me trying to port the whole compiler from JavaScript to Voxel. That would be quite fun. A bit repetitive, I think, in terms of just copying code, because it'd be very similar, but that would be fun to get that working. Yeah, if you like this video, please do like it. That I would really appreciate that, so that more people can see it and learn about the stuff that I do. You can check out the GitHub repo here at github.com/voxelius/voxel. Voxelius is actually a brand name which I created ages ago, which I have only used for very random stuff, but now I'm actually kind of formulating ideas around it. Please do give this repo a star, like I am doing now. And yeah, feel free to contribute, because the more people learning how to use Voxel, the better, I guess. Yeah, and looking forward to see you again soon in another code session video. And yeah, I might do a LiveG video on the LiveG channel at some point soon. I know it's been a while. I haven't abandoned LiveG. Hang on. I am daily driving it on my laptop. This is the framework laptop that I got. As you can see, I've got some cool LiveG stickers. And I'm daily driving LiveG.os now, so it's not like I've abandoned LiveG.os at all. This is just a side project to a side project to a side project, really. And LiveG.os is constantly getting improvements, because I have to use it in my laptop now and experience all its bugs. But yeah, I think that's about it for this video. Hope you enjoyed watching. I know it's been an hour and a half of me constantly, mostly explaining things. I think a good I'm gonna guess 45 minutes or half of this video has been me actually explaining stuff in this notebook. But apart from that, yeah, I hope you enjoyed it. Please do comment anything which you'd like me to talk about, and I'll be happy to do it. But yeah, thank you for watching, and I will see you later. Bye.